How do you map a place from which no traveler can ever return? For decades, we thought it was impossible. But now, scientists are starting to see the unseeable. Not by looking for something trying to escape, but by listening to the silent, invisible echoes of their most cataclysmic moments. We're on a cosmic detective mission to solve this very puzzle. If you want to see how we're peeling back the layers of reality's greatest mystery, hit that subscribe button and join us. It's one of the first, most fundamental rules you learn in any astronomy class. Nothing, not even light itself, can escape the gravitational pull of a black hole. Once something crosses that invisible line, the event horizon, it's gone from our universe for good. It is the ultimate one-way street. This gives us a deep, almost philosophical problem. For decades, the inside of a black hole was purely the stuff of math and imagination. But that's starting to change. The answer, it turns out, is found in the tremors black holes send through the very fabric of space-time itself. In this video, we'll gather the clues, explore the mind-bending theories, and see how we are finally starting to understand what truly lies inside a black hole. To get a grip on just how tough this problem is, we need to start with the beautifully brutal picture of a black hole painted by Albert Einstein's theory of general relativity. Picture a star, way more massive than our sun, running out of fuel. Its nuclear furnace sputters, and the immense gravitational force of its own mass is no longer held back. The star begins to collapse in on itself, catastrophically. As all that matter gets squeezed into a smaller and smaller space, its density goes through the roof, and its gravitational pull gets insane. Space-time itself, which Einstein showed us is a dynamic fabric, starts to warp and curve around this collapsing mass, like a bowling ball on a rubber sheet. As the collapse goes on, the curve gets steeper and steeper until it effectively closes in on itself. At this point, a boundary forms, the event horizon. This isn't a physical surface you could touch, it's a theoretical line in the sand. It's the point of no return. To escape a massive object, you need to hit its escape velocity. For Earth, that's about 11 kilometers per second. For the Sun, it's over 600. At the event horizon of a black hole, the escape velocity is 299,792 kilometers per second, the speed of light. Since nothing can travel faster than light, anything that crosses the horizon is trapped. Not just matter, but light itself. If you were inside the event horizon and pointed a flashlight away from the black hole, the photons would get dragged right back down. This is why black holes are black. They don't emit or reflect any light, which makes them invisible. According to general relativity, all the matter that made the black hole and everything that ever fell into it keeps getting crushed by gravity into an infinitesimally small, infinitely dense point at the center, the singularity. Here, at this single point, our known laws of physics don't just break down, they scream for help and then fall silent. Density and space-time curvature are infinite, and our math completely fails. For most of the 20th century, this was the picture. The inside of a black hole was empty, warped space-time, and a singularity where physics stops making sense. And because of the event horizon, this broken piece of reality was forever hidden from us. It was a perfect cosmic crime scene, with a suspect, the singularity, that could never be questioned, and a boundary, the event horizon, that locked away all the evidence. So for the longest time, asking what was really inside was basically philosophy, not physics. How could you ever test a theory about a place that by definition can't communicate with the rest of our universe? It seemed impossible. But science has a habit of turning the impossible into the merely difficult. If we couldn't look inside the prison, maybe we could learn something by listening for the tremors it sends out. For decades, black holes weren't much more than elegant scribbles in Einstein's equations. The first step in our detective story wasn't to look inside them, but to prove they were even real. Since they're invisible, astronomers had to become cosmic sleuths, searching for their gravitational fingerprints on the universe around them. The first big clue came from watching stars. In the heart of our own Milky Way, astronomers tracked stars for decades. They saw stars, like one called S2, whipping around a patch of seemingly empty space at incredible speeds, completing an orbit in about 16 years. The only explanation was that they were orbiting an unseen, unimaginably massive object, a supermassive black hole we now call Sagittarius A star, with a mass 4 million times our Sun's. That work was so important it won the 2020 Nobel Prize in Physics. Other clues came from the violent death spirals of matter getting too close. Gas and dust form a swirling, superheated structure called an accretion disk. As this material spirals inward, friction heats it to millions of degrees, causing it to glow brightly in X-rays. Telescopes could see these brilliant disks even if they couldn't see the hole itself. Sometimes, powerful magnetic fields launch colossal jets of particles from the black hole's poles at near light speed. Seeing these jets was more strong circumstantial evidence. But these were all indirect clues. We were seeing the effects of the black hole, not the black hole itself. The real breakthrough, the first time we truly saw the beast, came in 2019. The Event Horizon Telescope, or EHT, accomplished something monumental. The EHT isn't a single telescope, but a global network of radio telescopes, all synced up to create one Earth-sized virtual observatory. This incredible power allowed them to peer 55 million light-years away to the galaxy Messier 87 and capture the first-ever direct image of a black hole silhouette. What we saw wasn't the black hole, but its shadow cast against the glowing backdrop of its accretion disk. It was a perfect ring of light, bent by extreme gravity, surrounding a dark circular void. This image was a stunning confirmation of Einstein's theory. The size and shape of that shadow matched the predictions of general relativity with breathtaking precision. We were seeing, for the first time, the edge of space-time, the event horizon. But even this only showed us the boundary. It didn't tell us what was on the other side. To get closer to the truth, we needed a new sense. That new sense arrived on September 14, 2015. On that day, 2 giant detectors in the US, part of the LIGO experiment, felt a tremor. It wasn't an earthquake, it was a ripple in space-time itself. This was the first direct detection of gravitational waves. Einstein predicted that when massive objects accelerate, they create waves in space-time, like a boat makes waves in water. For a century, this was just an idea. The waves were thought to be so faint they'd never be found. But LIGO, a marvel of engineering, measured a distortion in space-time thousands of times smaller than an atom's nucleus. The signal LIGO detected, GW15094, was the unmistakable sound of 2 black holes, each about 30 times the mass of the Sun, spiraling into each other and merging over 1 billion light-years away. This threw open a brand new window on the cosmos. We had learned to listen to the universe. And this is where our detective story takes a crucial turn. The gravitational wave from a merger has 3 parts: the in-spiral, the merger, and the ring-down. The ring-down is the key. After the 2 black holes combine, the new, larger black hole is distorted. It quivers and vibrates, shedding energy as gravitational waves until it settles down. This is the ring-down. It's like striking a bell. The sound it makes tells you about the bell itself. In the same way, the ring-down waves are a direct probe of the new black hole. According to the no-hair theorem, a stable black hole is a cosmic minimalist. It can be described by just 3 things: mass, spin, and electric charge. All other details, the hair, of what it was made from are supposedly lost forever. By analyzing the ring-down waves, scientists can measure the mass and spin of the new black hole. More importantly, they can check if the signal matches the no-hair theorem. A black hole should ring like a pure tone, with specific notes determined only by its mass and spin. If we heard something different, some weird dissonance, it would be revolutionary. It would be evidence that black holes have more structure, more hair than Einstein allows. It would be our first real clue that something other than a singularity lies within. For years, the signals were too faint to pick out the subtle overtones. But as detectors have improved, we've started to hear them. Analysis of events like GW15094 and the much clearer GW25014 have found evidence not just of the main tone, but of at least one overtone as well. So far, every observation has perfectly matched the predictions of general relativity. The bells are ringing exactly as they should. But this very act of listening has changed the game. We now have a tool, gravitational wave spectroscopy, that can actually test our theories about the hidden interior. The prison walls are no longer completely silent. We found a way to listen for the echoes from within.
The crazy thing is, so far, every black hole we've listened to is ringing exactly like Einstein said it would. And that's both a huge triumph and a new puzzle. It tells us that from the outside, they're as simple as general relativity says. But it deepens the central mystery, what happens at the very center. Most physicists see the singularity not as a real thing, but as a warning sign that our theory is broken. When you get infinities in your equations, it's a red flag that you're missing something big. To solve this, we need to go beyond Einstein and into the weird world of quantum mechanics. We need a theory of quantum gravity. For decades, theoretical physicists have been cooking up candidates, each offering a bizarre new picture of what replaces the singularity. These ideas were once pure speculation, but now, with gravitational wave astronomy, they're becoming testable. It's time to meet the suspects in our cosmic whodunit. Our first suspect comes from one of the most famous and controversial ideas out there, string theory. It proposes that everything is made of tiny, vibrating strings of energy. Different vibrations create different particles. So what does string theory say is inside a black hole? The leading idea is the fuzzball. In this model, there is no singularity and no empty space. Instead, the black hole is a tangled, messy ball of these fundamental strings. The entire region is filled with this quantum fuzz. Crucially, there's no sharp event horizon. The surface of the fuzzball itself is the boundary. This neatly solves a huge problem called the information paradox, first pointed out by Stephen Hawking. He showed that black holes should slowly evaporate, and when they do, all the information about what fell in seems to be destroyed, which violates the laws of quantum mechanics. In the fuzzball model, information is never lost. It gets woven into the complex configuration of the strings. A fuzzball isn't a cosmic shredder. It's the universe's weirdest, densest hard drive. Our second suspect comes from a rival theory, loop quantum gravity, or LQG. Instead of replacing particles with strings, LQG quantizes space-time itself. It says space is made of discrete, indivisible chunks. There's a smallest possible length, so you can't crush something down to an infinitely small point. As a star collapses, the matter can't form a singularity. Instead, as it nears the maximum possible density, a huge outward pressure arises from quantum effects, halting the collapse. What forms instead is a hyper-compact object called a Planck star, and then it bounces. From the matter's perspective, the collapse and bounce are almost instant. But because of the black hole's insane gravity and time dilation, this bounce takes an extraordinarily long time for us to see. What we call a black hole could be the super slow motion replay of a bounce that will complete itself billions or trillions of years from now. Some theories even suggest the bounce could create a white hole that spews matter into a brand new baby universe. Suspect number 3, the holographic principle, and the 2D illusion. Our final suspect is maybe the most reality-bending of all. It's a radical idea called the holographic principle. It grew out of studying black holes and led to a startling hypothesis. Maybe our three-dimensional reality is a kind of projection, a hologram of information that's encoded on a distant two-dimensional surface. It's counterintuitive. You'd think a bigger room could hold more information, not just a room with bigger walls. In the context of a black hole, this principle suggests that everything that falls in, all its 3D information, is perfectly encoded on the 2D surface of the event horizon. From our perspective, it looks like an object falls through the horizon into a 3D interior. But according to this principle, that's an illusion. The information never truly leaves the boundary. So asking what's inside is like asking what's inside the 2D film of a holographic image. The 3D image is the content, but the information itself lives on the 2D surface. So there's our lineup: the fuzzball, a tangled ball of strings; the Planck star, a bouncing quantum object; and the hologram, a 3D illusion. For years, these ideas have been battling it out on chalkboards, but now the game is changing. We finally have the evidence, gravitational waves, to put these suspects on trial. Okay, fuzzballs, Planck stars, holograms, it all sounds like great sci-fi, right? But here's the amazing part: we can actually test these ideas. The ultimate laboratory is the ring down of a black hole merger, and our primary tool is gravitational wave astronomy. The core idea is to look for tiny glitches, tiny deviations from Einstein's predictions. Each of our suspects should leave a unique fingerprint on the gravitational waves. Take the fuzzball. It isn't an empty void, it has a physical surface. This surface could absorb and re-emit gravitational waves differently than a perfect horizon. Some models predict this could create echoes, faint, repeating gravitational wave signals that follow the main event. Finding echoes would be a smoking gun for new physics. Now the Planck star. Having a physical object at the core instead of a singularity could introduce subtle distortions into the ring-down signal. The bell wouldn't ring with a perfectly pure tone. The frequencies might be slightly different from what general relativity predicts for a hairless black hole. Even the abstract holographic principle could be tested. Extremely precise measurements of the ring down could let us count the black hole's degrees of freedom, testing the idea that its information scales with the surface area, not the volume. So far, the evidence is on Einstein's side. With every new detection, from that first one in 2015 to the flood of clearer signals we're getting now, the ring down has matched general relativity with incredible fidelity. We haven't detected any definitive echoes or dissonant notes. But this is just the beginning. Our current detectors are still in their infancy. The fourth observing run of LIGO, Virgo, and Cagra, which began in May 2023, is detecting mergers with amazing clarity and frequency, giving us a treasure trove of data. The future is even more exciting. Next-gen ground-based observatories like the Einstein Telescope and Cosmic Explorer will be 10 times more sensitive. And in the 2030s, the Laser Interferometer Space Lancer, or LISA, is set to launch. LISA will be a space-based detector with arms millions of kilometers long. It will be sensitive to low-frequency gravitational waves, like those from merging supermassive black holes. These signals will be incredibly loud and long-lasting. With LISA, we won't just hear one note from the ringing bell, we'll hear a full symphony of overtones. We'll be able to map the structure of black holes to an astonishing degree. If there are any deviations from Einstein's theory, any signatures of fuzzballs or Planck stars, LISA will have the best chance of finding them. We've moved from asking what if to asking how can we look. We've built the tools to turn a philosophical question into an observational science.
This journey to the heart of a black hole is pushing the limits of what we know and what we can imagine.
We're moving from a universe we see to a universe we must listen to, decoding the secrets hidden in the vibrations of space-time. If this dive into the cosmos has expanded your mind, hit that subscribe button and ring the notification bell so you don't miss our next adventure. And now we want to hear from you. After hearing the evidence, which suspect do you find most compelling? Is a black hole a fuzzball of tangled strings, a bouncing Planck star, or is it all a holographic illusion? Let us know your theory in the comments below. We love seeing your perspectives on these incredible ideas, and a quick like on the video really helps our community grow. And speaking of cosmic wonders, if you want to explore some of the strangest structures out there, you should visit our previous video, The Most Bizarre Galaxies in Existence, where you can learn all about the NGC 6000 galaxy. So, how do we know what's inside a black hole? The honest answer is, we don't. Not for sure. Not yet. But we're no longer completely in the dark. We've gone from a state of total ignorance to an active investigation. We've laid out the central paradox, the epic clash between Einstein's smooth geometric universe and the messy, quantized world of quantum mechanics, a fight that comes to a head in the infinite singularity. We've learned how to be cosmic detectives. We found the black hole's footprints by tracking the dance of stars and the glow of doomed matter. With the Event Horizon Telescope, we captured the shadow of the beast itself. And most importantly, with gravitational waves, we have learned to listen. We can hear the cosmic bells ringing when black holes merge, and their precise tone is our first real physical probe of their fundamental structure. This new ability to listen has turned abstract theories into testable hypotheses. The ideas of string theory's fuzzballs, loop quantum gravity's Planck stars, and the mind-bending holographic principle aren't just equations anymore. They are now competing suspects, each predicting subtle signatures, echoes, distortions, new harmonies that we can actually search for in the data. For now, the verdict favors the classical picture. Black holes appear to be as simple and hairless as Einstein predicted. But we are standing at the dawn of a new age of precision. With future observatories like LIGO on the horizon, our hearing is getting sharper every day. We'll be able to listen to the symphony of merging black holes with ever greater fidelity. What we are doing is peeling back the layers of reality itself. We are hunting for an answer that forces us to confront the fundamental nature of space, time, and information. The final answer may not come tomorrow, or even in the next decade. But the path is clear. The detective story continues, written in the language of vibrating space-time. And the solution, when we finally find it, won't just tell us what's inside a black hole, it will likely reveal the next chapter in our understanding of the entire universe. The greatest mystery remains, but for the first time in human history, we have the tools to one day solve it.